Okay, so last time we talked about Newtonian particles. Today I want to talk about fractals. Let me get a share screen going here. Okay, so we might ask the question, what is the length of the coastline of Maine? We put a ruler up along here and we'd say it's 5 inches long, and we'd convert the inches to miles, and we'd have the length of the coastline. But as we go into higher and higher detail, we start to see more of this stuff along the coast, and as our ruler gets smaller and smaller, we see more and more detail, and our coastline is a lot longer. So the length of the coast of Maine depends on the length of the ruler that you're using to measure it, because at higher and higher resolutions, you see more and more detail that looks similar at whatever scale you observe it. Our author seems to be somewhat obsessed with the Koch Snowflake, the Koch Snowflake, which is an example of a fractal. We start off with a triangle, add stars, and continually increase the length of this coastline of the Koch Snowflake. What we're doing with the Koch Snowflake, we're taking each of these lines, we're dividing it into a third, we're displacing the center so that we get an equilateral triangle with sides that are exactly 1/3 long. And we do this recursively with each of the straight edges of our Koch Snowflake. The concept of fractal geometry was kind of pioneered by Mandelbrot, a French and American mathematician. He was an IBM fellow in the 50s. He was one of the first to use computer graphics to both create and display fractal images, and he discovered the Mandelbrot set in 1979, which showed how very simple rules lead to extremely complex visual behavior. And also, he recognized that natural phenomena that appeared rough or chaotic actually had a quantifiable degree of order. And this was discussed in a book, The Fractal Geometry of Nature. So this is the Mandelbrot set, which maybe we'll talk about later. As you zoom in on this Mandelbrot set and zoom further in and zoom further in, you see more and more self-similar detail. Notice here's this bulb here, and here it is appearing again as we've zoomed here to here to here to here, 2,000 times zoom. Similar features appear in ice crystals and electric sparks and frost on a window. These are actually pictures of something called the spiders of Mars, that are a phenomena that occurs when the CO2 layer that freezes out in the winter melts in the springtime. So let's go back and look at this Koch Snowflake, where we take a single line, break it in thirds, and move one point up, making 2 more sides of a third. And I want to talk a little bit about what we mean by the fractal dimension. So let's talk about objects whose dimensionality we can agree on. A line is a 1-dimensional, a square is 2-dimensional, and a cube is 3-dimensional. And so if I consider dividing each of these by 1/n, where n is a 3, the line turns into 3 little segments. The square turns into 9 little segments, and the cube turns into 3 times 3 times 3, 27 little objects. So with the line n dividing it into thirds, we have n to the 1 is 3. With the square, we have n to the 2 is 9. And with the cube, we have n to the 3 is 27. And since the whole is the sum of its parts, the whole is the number of items we get, 27, and we're dividing it into n to a power, that power being the dimension of the object. We can then solve this for d, taking the logarithms and recognizing that log n raised to the d is d log n. We have that the dimension of our object is log of k over log of n. So for the cube, we have log of 27 divided by log of 3. This is 3.29 divided by 1.09, which is 3. The cube has a dimension 3. The cube is a three-dimensional object. So let's look at the Koch Snowflake. Here again, n is 3. We're dividing it in thirds. But in this case, we're creating 4 new objects, the 4 segments of the Koch Snowflake here. So our dimension is log of 4 divided by log of 3, which is 1.26. The dimensionality of the Koch Snowflake is not 2D, but it's 1.26D. Another one that our author plays with is the Sierpinski Gasket. Here we take a triangle, we divide its sides in half, and this makes 3 new objects. So here n is 2 and k is 3 new objects. So the dimensionality of the Sierpinski Gasket is 1.58. Here's some volumetric examples. This is kind of a 3D version of the Sierpinski Gasket. If it's a triangular based solid, here in this, we're dividing it in 2. We're making 4 new objects, 1, 2, 3, 4. So the dimensionality of this object is 2. It's not a 3D object, it's a 2D object. And here's another more complex example. So the idea here is that fractal curves have a dimension that's between 1, where they would be very smooth, i.e. straight, and 2, where they're very rough. And fractal surfaces have a dimension between 2, which is going to be a smooth surface, like a square, and 3, where they're very rough, like our Sierpinski Gasket. So we can use these fractal curves and surfaces in synthetic scenes, in other words, video games, where we want, say, a skyline or a terrain that has some controllable degree of realistic and random roughness, i.e. a particular dimension. So how can we generate such a terrain? Well, one approach is midpoint subdivision. Given 2 points, we can find the midpoint, p plus q over 2, and we can displace that point some distance perpendicular to it with an amount that's generated by some pseudo-random number generator, preferably a Gaussian random number generator. As you continue the subdivision, then you take these 2 lines, subdivide it, and displace it. Take these 2 lines, subdivide it, and displace it. We can reduce the displacement of each iteration by reducing the variance of our random number generator or the amplitude of the generator. Now, you're probably familiar with random number generators that generate numbers in a range from 0 to 1, here scaled so that they go from -1 to +1. But a Gaussian generator returns numbers in a bell-shaped curve, a bell-shaped distribution. So a Gaussian random number generator is going to generate numbers out here, but less frequently than it's going to generate numbers up here. If we make the variance proportional to the length raised to some power that is a function of the dimension, 2 times 2 minus d, we obtain curves like this. For a small d, we get kind of a smooth surface. And as we increase the dimension, we get more and more jagged curves. And actually at a d of 1.5, we get what's known as Brownian motion. It's kind of a classic, it's the random movement of particles that are floating in a fluid. They bounce around. This is how they discovered atoms. So a simple algorithm for generating this, we have our nn, which is 3. So we're going to divide this into nm different intervals, raise the 2 to the nn power. We can set our endpoints here for the 2 points. And then we start this almost recursive algorithm where we divide the interval in 2, set our variance with this power scale, and then set the midpoint of our interval as being the average of the two points on either side of it, with a random variance added to it. Basically what we're doing, we're starting off with just the values of the 2 points on the end. We're averaging them to form the point in the middle, adding a little random into it. Then we're taking these 2 points, averaging them to get this point with a little bit of variance, averaging these 2 to get 0.6, again with some variance, and then repeating the average of these 2 for 7, these 2 for 5, these 2 for 3, and these 2 for 1. I'll let you walk through this hand calculation here where I work out the different steps, but this generates something that looks like this. I kind of got tired of doing it in WebGL, so I did it in Unity, but here's Unity generating a randomly generated skyline with these with that subdivision algorithm. So that's all kind of interesting. We can, if we want to, generate a skyline that from this subdivision algorithm. But we can also extend this method into 2 dimensions and make fractal mountains. And here's what fractal mountains can look like. So here's a little, this is a fractal landscape made with basically a 2-dimensional version of that algorithm that I just showed you. And if I run this again, I'll get a different landscape. And if I run it again, I get a different landscape. But in each case, it looks kind of realistic in the sense that it's a randomly generated, but self-similar, a fractal surface. So one of many algorithms for generating fractal mountains is the diamond square algorithm. And with this algorithm, we start with just 4 corners, and we can specify the separate heights of the 4 corners. And then we fill in intermediate values by a 4-corner midpoint division, kind of a 4-corner analog to what we did here in the 1 dimensions. Because we're subdividing it, it's useful to make our grid a power of 2, power of 2 plus 1 points. If you think of n equal 3, this gives us points 0 to 8. 8 divided by 2 is 4. 4 is the middle of those 9 points that we're using here. So starting off with 1024 width, 1024 height, and our data This is a two-dimensional data array similar to what we did when we were displaying the mesh. In fact, I'm using the same tools to display this as I did to display the mesh. Now, as we sample here, we're going to have two different functions. One for sampling the four corners. So we have to be able to say at a particular position in our checkerboard, what is the value of the point there. And we would also like to be able to wrap around our checkerboard grid. In other words, we want this to be a toroid. We want, as you move out of the right, you want it to come back in on the left. As you move out of the left, you want to come back in on the right. And the same with the top and bottom. So we have this little piece of code that just, if we're ever outside the width, we sample from that position minus the width, and same for up and down and right and left. We also want to be able to set a point at a particular X and Y value. And again, with the same sort of wraparound potential. So here we would have X and Y and the value that we want to set there. And we'd assign to our data X, Y, Z at X, Y location a vec3 of X value and Y. So schematically, what we're doing here with the diamond square, we start off with our checkerboard of points, power of 2 plus 1 on each side. And we start off with the square. So we're taking the 4 points on the corner, and we're defining the midpoint here, the point that's in the middle, halfway between those. Then we do the diamond, which is now where our sample points are the 4 here, and here's where the wraparound comes in. When we're sampling this point out here, we're actually getting this point here, but we take those 4 points and we define the point in the center here. Then we do a square, again, taking these 4 points to generate this one, these 4 points to generate this one. Then we do a diamond, again with this wraparound, but these 4 points now define this one. And we can keep repeating this diamond, square, finally diamond, and finally we've defined all the points. So we need a couple of little routines here. If we're going to sample a square, we have the X and Y location of the point that we're generating, the size, which is how far it is from A to B, and the value that we're going to put there. This is going to be a randomly generated point. So for the square, I'm going to sample at X minus half the width, Y minus half the width, that's the A point. The B point is X plus half the width, Y minus half the width, and so forth for C and D, the other corners. And then we use our set sample to assign to X and Y the values of A, B, C, and D averaged, plus this random value that we're offsetting it by. The diamond algorithm works similarly. We have A, B, C, and D, and the point in the center here. And now A is going to be X minus half the width, half the size. Over here, B is going to be X plus half the width. And C and D are X, Y minus, and Y plus the half width. And again, we set the sample at A plus B plus D divided by 4 plus the randomly selected value. So our diamond square algorithm consists of a sequence of square and diamond operations. This would be one iteration of it where we do a diamond, a sample square, and then we do a sample diamond. Again, with the these are our random numbers, FRAND with some scaling factor. And the overall diamond square algorithm takes width and height, and it generates it generates the full diamond. It generates the full grid. FRAND, which I mentioned, is a Gaussian generator. This is a little snippet of code that takes our normal random number generator that generates 0 to 1 numbers and does some magic to generate a Gaussian distribution with a variance of 1. So I'll show you the fractal terrain one more time here. This is set up so that I can fly around in the fractal terrain. And it's lit and shaded and has shiny spots, and it's shaded. And every time I press this, I'll get a different random terrain. But I'm starting off with the 4 corners of this square and generating random terrains by that diamond square algorithm. So I'll stop there. I'll end the lecture with that. I'll post these notes and the sample program. And I'm going to end the recording now. So see you all in class. Bye.